Hey guys, so today we're talking about uniform acceleration equations. So this is a little bit of a review of some stuff we've already done, plus some new stuff that we haven't done yet. So it'll be a little bit of a combo, but we need a refresher on these equations and we need to know how to apply these equations in order to do projectile motion. So first thing we need to pay attention to, this word uniform here, we remember this means constant. So there we go. All of these equations that we're going to be looking at today are all equations that only work for constant acceleration. So a lot of these things that we're going to be looking at, you see down here underneath these equations are these conditions, and we're going to be looking at those conditions. And one of the conditions for these equations to work is that we have to have constant acceleration. Lucky for you guys in this class, we will always be using constant acceleration, so that's not something that you have to really be worried about in this class, but it's a good thing to note in terms of just like the physical world and what we're actually doing here. We are going to be talking about constant acceleration. You could talk about non-constant acceleration, but we're not going to be getting to that level in this class. So let's get started with some of our main equations. I'm going to start right here in the middle with velocity. So we remember what our equation for velocity is. It's displacement, this D here means displacement, divided by time, because it's how far you travel in a certain amount of time. And our units for that are going to be the units of displacement, which are meters, divided by the units of time, which are seconds. If you wanted to do not these units, you could. We're mostly going to be using meters per second in this class, but you could use some other units of displacement divided by some other units of time. So something like miles per hour or something like that is also totally great, but just we probably won't use it as much in this class. So that's velocity. That's a pretty easy one. The condition for this one is that this is v average. This is our average velocity. This equation does not give you your instantaneous velocity. It gives you your velocity when your velocity is constant. Next, let's look at acceleration. Acceleration is defined as a change in velocity over time. So we write it like this. We write a delta v, this triangle is a delta, divided by t, which is time. This delta right here just means change in. So this is a change in velocity divided by time. The other way that we can write this, which we're going to be using mostly in this class, is v final. That's our final velocity. We write it as vf. You can see that down here under the conditions. Vf is the final velocity, minus v initial, where I stands for initial velocity. So this is our velocity at the beginning and our velocity at the end. And you divide that by time. Our units for acceleration are going to be the units of velocity, meters per second, divided by the units of time. And you guys might remember this. We can actually combine these seconds right here. They don't cancel out, they get combined. So then we normally write this as meters per second squared. And those are our typical units of acceleration. Again, could you do like a different unit for velocity divided by a different unit for time? Sure, you totally could. You could do something like, if you were doing miles per hour as your units of velocity, you could divide that by any unit of time. So maybe it's miles per hour per days. You could do that. Totally works. Totally checks out. The most important thing is that in the top, you have some sort of units that are velocity units, and in the bottom, you have some sort of units that are time units. But this is probably going to be the one that we're primarily using in this class. Just like this is going to be the one that we're primarily using in this class. So that's acceleration and velocity. Conditions on this one. This is also the average acceleration. We'll be pretty lazy with that average subscript just because, again, you're going to be using almost always constant acceleration in this class, so you won't really have to think about average versus instantaneous. But this is technically a average, and if you had a changing acceleration, this equation wouldn't work. So then our final equation, this one's a new one. It's so exciting. So our new equation is going to be a new way of finding displacement with respect to acceleration. So here's our equation. Stick with me. It's going to be 1/2 times a, that's a is for acceleration, times t, that's for time, squared. That's it. Bum, bum. new equation. Yay! Super exciting. So this is our new equation for displacement, and we can find displacement in terms of acceleration and time. This is a super useful equation. We're going to be using it a lot, and you guys are going to be doing some practice problems with it. We could take the time to talk about where it comes from, but this is really where you have to land, is understanding and really knowing this equation. So the units of displacement, we already know that those are meters. But we can also see that they're meters here because we have 1/2 times the units of acceleration are meters per second squared times a time, which gives us seconds squared. And so the second squared on the bottom and the second squared on the top cancel out, and you're just left with meters. Yay! So those are the units that we're mostly going to be using. Again, you could use some other units like miles or light years, but in this class we're mostly just going to be using meters. So the conditions for this equation are really important. This equation only works if the object starts from rest and if it has a constant acceleration. So if it starts moving, this isn't going to give you an accurate equation for your displacement. And if its acceleration is changing, this equation isn't going to work. But in general, if it starts from rest and if it has a constant acceleration, which most of the problems in this class that we do will meet these two conditions, then you can go ahead and use this equation. So all of this stuff is very exciting because now we have new ways to find all of these different variables. So if we look down here, we'll keep these equations in view. We can rearrange each of these equations to find new things. So first, to find displacement, well, we have this original equation that we have right here, 1/2 at squared. Yes, our new best friend of an equation. But we could also rearrange that velocity equation up here to get a new equation for displacement. So if we multiply both sides by time, then we can have d equals v average times time. Yay! That one's super great. And you can see this equation down here in this box is exactly the same as that equation up there. We just rearranged it. We can do the same thing with different ways to find velocities. So the first way we know is that v average equals d over t. But the other thing we can do, this is tricky, so follow along here. We know that a average is v final minus v initial divided by time. If the object starts from rest, that means your v initial is 0. So we can write this out like this. V final minus v initial over time. If your object starts from rest, then this v initial is 0. And so all you're left with is v final divided by time. So then you could rearrange that to get that v final equals acceleration times time. Again, this only works if your v initial is 0. This is one of those conditions, so it has to start from rest. Just like this equation for displacement also has to start from rest in order to work. Then we have different ways of finding acceleration. So our first one is the one that we have written there, vf minus vi divided by time. And then our second way is we can rearrange that other equation that we have for displacement now. So we could say, let's see, how do we do this? We have, I'm going to multiply both sides by 2, so 2d. I have to do all my steps, guys. I did not rush through these kinds of things. And then you can divide both sides by t squared to get a by itself. So a equals 2d divided by t squared. Yay! But once again, you can see that all of these equations are really just the equations that we had above, but just rearranged slightly for different variables. So that is kind of these equations and an overview of these equations. So now, this is kind of a side note, but I think it's really important because it's going to blow your minds and it's going to be awesome. Remember when we made displacement versus time graphs and velocity versus time graphs? I do hope you remember because that wasn't that long ago. So let's draw one right here. So here's our displacement in meters. Here's our time in seconds. And then we'll make a velocity versus time graph. So this is our velocity in meters per second. And this is our time in seconds. Do you guys remember that when things were accelerating, when things are accelerating, that means their velocity is not constant. The shape of your displacement versus time graph looks kind of like this. And then when you did like your best fit equation for it, you found out your best fit equation, you probably used quad reg in your calculator, and it gave you some sort of equation that was like d equals, well, it gave you y, right? So we can write it as y. That's fine. So it gave you some sort of equation like y equals some sort of like a value times x squared plus a bunch of other stuff. Well, here's the cool thing, guys, is that this totally makes sense. If we look up at this equation right here, we have d equals 1/2 a times t squared. Well, that's what's happening down here. This y represents displacement because displacement is on the y-axis. This a here that your calculator gives you is representative of 1/2 times the acceleration. That's what that number that your calculator gives you is. So you could actually find the acceleration of an object just based off the equation that your calculator gives you, because it would give you this number, and then you could just find out that that's 1/2 a. And that x squared is going to be our t squared because it's on the x-axis. And then it gives you some other stuff too that's out there. Basically, in a short way of talking about that is that that's the kind of stuff that you'll see if a object is not starting from rest. Then the rest of that equation stuff applies there. But in this class, we'll only really be looking at objects that start from rest. So you can see how this equation from your calculator matches your graph. And that matches the equation that we just found. That's like the coolest thing. It's like things make sense. It's like graphs of things actually like totally relate to like what's going on in the world. It's awesome. So, and then if we look at our velocity versus time graph, so for something that looked like, for something that's accelerating, that has an acceleration, we remember it looked like this, right? And the slope of a velocity versus time graph is acceleration. So we know that the slope is acceleration. Well, that makes sense. When you did this, you probably used a linreg for a linear regression in your calculator, and that gave you some equation that looks something like this: y equals ax plus b. Okay, well, I know you're seeing it coming. I know you know what's about to happen. But this y here is going to be equal to your velocity, your final velocity, actually, because velocity is on the y-axis. That a right there is going to be equal to the slope of your graph, and we know that the slope of our graph is acceleration, and that x right there is going to be equivalent to time because time is on the x-axis. What? So you can see how that connects back to this equation, and this equation works with the graph. They all work together. The equation and the graph are both telling the same story about what's happening. So that's how we can represent these kinds of things graphically, is because their equations make graphs. So it's pretty awesome stuff. So I think that's all we have for today. Yes, it is. And then I'll see you in class tomorrow, and we'll do some practice problems using these wonderful equations.